All right, in this lesson we're going to take a little bit of a closer look at something called covalent bonding. Now, covalent bonding should be fairly familiar, but we kind of have to put this into context of the bigger picture, so let's do a bit of review. First of all, this blank, any substance with a definite composition involving two or more elements, you should probably recognize that as a chemical compound. This word definite, of course, this refers to some sort of a fixed proportion, right? So there's definitely some elements involved, and these elements are combined in a specific ratio, and that's again what we mean by definite composition. For example, sucrose is a chemical compound because, well, it's always made of C, H, and O in a very specific ratio, has multiple elements too. Also, table salt, which you probably recognize, is also sodium chloride because that, once again, contains multiple elements, in this case NaCl, in a very specific ratio. However, as a non-example, fluorine is not a chemical compound because it's just one element, right? That's not a actual substance that has more than one element. There you go, just one element. And finally, air in this case is not a chemical compound. It is composed of several different elements, right? Part of the original definition is that it involves two or more, but again, it's not exactly definite. Sometimes the percentage of oxygen is only 14%. Sometimes it's even lower at 9%, right? It kind of depends on the mixture. And so air is not a chemical compound. All right, let's take a look at the next one here. A chemical compound where its elements are covalently bonded. These are covalent or molecular compounds. Either one's fine. So covalent compound, molecular compound, they refer to the same thing. These are chemical compounds where its elements are covalently bonded. And of course, the elements in this type of bond are typically nonmetals. And for example, our friend sucrose, we saw that earlier, this is a compound first of all, but more specifically, it's a covalent compound because it's made of different nonmetals. So CHs and Os, again, all nonmetals. As a non-example, table salt is actually a compound, but it's not a covalent compound because it has metal and non-metals. Third bullet point here, a group of atoms held together by covalent bonds. This would be a molecule. You're generally probably familiar with this idea, right? It's a grouping of atoms together, but more specifically, this is one held by covalent bonds. You can see right here, this is an example of one molecule of sucrose, and then within it, you have a bunch of C's and H's and O's. This is the representative particle that shows how covalent compounds exist. And this, again, is one of those examples where, you know, there's only one of them. We can look at some other ones later on. But remember, the important thing is that this representative particle shows you how this molecule, or excuse me, shows you how any of these compounds exists in reality. And sucrose, as this example, is a compound that's represented by molecules. In contrast, what you see here as a non-example, table salt is a compound, but it's not represented by molecules because when it's something, it's an ionically bonded. It's actually represented, right? Table salt is a compound instead represented by something called the formula unit, right? So something represented by the formula unit. Now this is something that we'll get to later on, so we'll talk some more about it. But if you look over here on the right side, right, you don't really see just a single Na and a single Cl, right? You actually see a lot of Nas, which might be like the green, and then the purple or whatever might be the Cls. So there's two different elements exist, not as single groupings of like molecules, kind of like you see here with sucrose on the left, but instead as a bunch of Nas and Cls in this giant network. All right, so we'll talk some more about that later, and let's move on. First one right here. The written representation of a compound using element symbols and subscripts representing the number of atoms of each element. You see with examples that we saw earlier, that will be a local formula. Right? So the key word here again is generally formula, so you'll be asked for like, hey, what's the formula for this compound? This is the written way that we represent them. So instead of having to draw out a molecule every single time, we can just kind of boil it down to its essence, which is the C12H22O11. So that would be an example of the formula for sucrose. On the other hand, you have sodium chloride, which again, we've already talked about is not a covalent compound, but again, the key is that you do have a formula that you can represent it, and that'd be NaCl. So those are examples of formulas where it uses the element symbols and the subscripts to represent how many there are of each. And then finally, this is kind of a special category of molecular compounds, or at least with covalent compounds. These are molecules that are composed of the same element, like oxygen, hydrogen, and nitrogen, where they all exist as O2, H2, and N2, and not just O, H, or N by itself. We call these diatomic molecules. So these, again, diatomic, di meaning two, atomic referring to atoms. And these are molecules made of two atoms. So these diatomic molecules are specific to certain elements, oxygen, hydrogen being some of them. So this first little bullet point right here, the representative particle of O2 is still a molecule. right? Instead of being an atom, right? For example, if you just looked at regular old sodium by itself, sodium doesn't exist as a diatomic molecule, so it'd just be monatomic. That'd be an atom instead. But for oxygen, right, that exists as a molecule, not as individual atoms. And there exists a covalent bond between the atoms of oxygen. Why is that? Well, because it's got a bunch of, two nonmetals bonded together, right? Here's an oxygen, here's another oxygen bonded together. That's a covalent bond. But the one thing that we can't really kind of use appropriately here is that oxygen is not a, and I think this is the wrong word here, right? But actually, instead of the word I should be looking for is, oxygen is not a covalent compound, right? Oxygen is not a covalent compound. And why is that? Remember, the word compound refers to there being a fixed ratio of more than one element, right? 2 plus elements. This is still one element, right? So it's just oxygen, so it definitely doesn't have the label compound applied to it. Now, this is going to kind of break down, the next section here is going to break down how covalent bonds are formed. All right, so there's a bit of a process to this. When two individual atoms approach each other to form a bond, a system of interactions begin to develop. So let's try this out. The positive nucleus of one atom attracts the negative electrons of the other atom. So if you look over here on the right side, right, you have one atom, second atom. Here's the nucleus in the middle, it's positive. And as you can see right here, kind of with this sort of red thing, is that you kind of have this sort of attraction. So the positive nucleus being attracted, sort of this negative electron cloud. And then vice versa, this proton right here, this nucleus in the middle is positive, attracting the negative attraction over here from the cloud. So some attractions going on there. But at the same time, the positive nuclei repel, and also the negative electrons, kind of already hidden in there, but try that again, also repel. So the two things here are repelling are those like charges, the positive and the positive, as well as the negative and the negative. So when the bonds do eventually form, right, there's actually, again, going to be the system of attraction and repulsion going on, but there is still an optimal distance between the two atoms, where the attractions of the bonded atoms is maximized. All right. Therefore, bonding results in an atom arrangement that is more stable than as separate atoms. Right? So the idea here, again, is that when these two come together, there's going to be the optimal distance where the attractions are maximized and the repulsions, while present, is kind of generally minimized. And this overall system, this distance, anyway, of where attractions and repulsions interplay, we have the stability because these atoms are now bonded. So in this continuation of the discussion, this is going to be kind of a diagram that's worth breaking down. First of all, you notice that you have kind of two sort of axes. On the x-axis, this is the distance between the hydrogen nuclei. So let's say we have two atoms are bonded together. You can see right here, right, very far apart on the very far right of this. These two atoms are very far apart. They're basically not even interacting at all. And then as you kind of move towards the left, you get closer and closer. On the y-axis, we have something called potential energy. And this potential energy is that thing that sort of is there that because of the electrons have some sort of, interactions. And because the electrons, the way that they're arranged, they have a certain potential energy. And so the idea here is going to be kind of sort of opposites or sort of counterintuitive. But to kind of follow this process, what we're going to do is talk about how atoms bond by going kind of from the right to the left, right? So as you can imagine, you have part A, then part B, C, and D. So we're going to talk about this going from right to left. First of all, we're going to use this illustrative example of hydrogen, right? This is pretty much the most advanced and the most difficult bond that we're going to really need to understand. But basically with hydrogen, we have at point A here is that there's no interaction between my two atoms, right? The distance is really far away. So we're very far to the right on the x-axis. And so if you also notice, the potential energy is basically at 0 kilojoules per mole. This is considered high because individually each atom has a potential energy. And the idea is that when they bond, the potential energy is lowered. All right, so let's go ahead and start bringing them together. So if I make my distance, right, a little bit smaller, so I keep moving towards left here from point A to point B now, these two atoms, which are really far apart, are now a little bit closer to each other, right? So again, as they kind of get closer to each other, those attractions begin to form. Repulsions are present, but we can kind of consider them to be negligible at this point. And then you can tell right here, potential energy is decreasing, right? Because it started off at 0, kind of this line right here in blue, and now from here to here, right, you can tell that potential energy has dropped. Therefore, the attractions are allowing the stability to be better. Let's go move to where we're at point C. So continuing on this process from point B to point C, right, going from here to here. What do you notice? Well, the distance, right? So we're no longer kind of this sort of vague, kind of maybe sort of attraction, but now we're kind of real close to each other, right? There's a very specific amount of distance between these two. Turns out it ends up being 75 picometers. And that distance of attraction is known as as we call it, the optimal distance, where you have lots of attractions, right? But the repulsions are still kind of low. And with this optimal distance, that potential energy is the lowest it can possibly get. So this is kind of like a nice little kind of valley here, right? You can see that, if we're too far away, there's some attractions, but we can definitely do better by bringing them closer together. And if you bring it close enough, right, you have that perfect distance. Because once you kind of move away from that, meaning you kind of continue to the left, right? So we're getting closer and closer to our distance is 0, right? You can see right here what happens to your potential energy. Well, again, we talked about this sort of interaction where it's like getting better, but then you can also have too much of a good thing. So as you kind of bring things closer and closer together, what happens? Your attractions are present still, but repulsions have increased significantly, right? So those negatives, like they're kind of actually getting closer and closer to practically on top of each other. Same thing with the positive nuclei. And so as a result, right, what do you notice about your potential energy the closer and closer you get? So these two things, right, as you can see, the potential energy goes higher and higher and higher. So again, we can have too much of a good thing. While being really far apart, right, there's not really any gain to it. We can see that, oh yeah, if we bring it closer together, the potential energy drops. But again, if we keep bringing it closer and closer, we can do even better and have the potential energy drop all the way from 0 down to here. But again, there's too much of a good thing. So if you have too close of atoms, the potential energy continues to increase because those repulsions become bigger and bigger and therefore make it less and less stable. All right, let's kind of break the rest of this down. First of all, with orbital overlap, what we talked about here is basically, again, using H2 as an example. We see here that the valence electrons, right, of hydrogen, of atoms are involved in bonding specific with hydrogen. There's only one electron, and these electrons are located in orbitals. Generally speaking, it's the outermost orbital. For hydrogen, there's only one electron, so its outermost orbital is that single electron in that spherically shaped 1s orbital. So you can see right here, right, we have our nuclei. Here is a single hydrogen atom. Here's a second hydrogen atom individually. You notice you have that nucleus in the middle, and you have that spherical electron cloud where there's an electron floating around. Same thing over here. But then when the two atoms bond, they overlap, and that overlap is where you form that region where these shared electrons are. So somewhere in here, you can kind of see there's a bit of a darker sort of semi-shaded area there. That area is where the bond is because orbitals have overlapped. So the main takeaway here is that the reason why there's any bonding, or at least part of what forms the bond, is that space where there's an overlap. That overlap, again, is actually where the orbitals have overlapped. All right, let's try this one out. Bond length and bond energy. The distance between two bonded atoms at the lowest potential energy. All right, that distance, again, is considered the bond length. Okay, so it kind of makes sense, right? Bond length referring to a distance. But then also we have to consider this thing called a bond energy. So the bond energy, this is the energy required to break bonds into individual neutral atoms, and this is known as the bond energy. Right? Now, this is basically a measure of strength, and this right here, let me actually put this in. This is measured in units of kilojoules per mole. So we talk about having a mole of these bonds or a mole of these molecules, and then effectively we try to put enough energy in it to break. So we don't really have a device that we can just put into a sample of, say, hydrogen and say, oh yeah, that is going to tell me that this bond has a certain strength, right? We can't just put something like a device in there and just have some meter that measures it out. We kind of have to kind of go an indirect way and say, okay, how much energy does it take to break a bond apart? That tells me how strong the bond is. So generally speaking, if you have a high amount of energy is needed to break a bond, the bond is considered strong. Whereas on the other hand, if a low amount of energy is needed to break a bond, the bond is considered weak, right? And you can see here there's some very distinct patterns. So I'm going to highlight a few of them for you. This chart right here is kind of nice because it sort of breaks down, again, some similar things. You can see HH right here, FF, CL, CL, all the way down to II, right? Those are same elements being bonded together. You can see what happens is that basically when it comes to bond length, right, you get 75, 142, 199, 220. So these kind of increasing, getting bigger and bigger, right? The bond length is getting bigger and bigger. What happens to your bond energy? Well, broadly speaking, right, it's not exactly perfect, but again, the further away they are from each other, the weaker the attraction is because the less energy required to break it down. Let's go and try this one out. This one's a little bit more consistent, right? A little bit less sort of kind of jumpy. But again, as you notice, the bond length between HF all the way down to HI. Remember, these are actually all elements in the same column of the periodic table. So HF, HCl, HBr, HI, all these halogens. These actually, again, you can tell the bond length kind of increases pretty steadily. What happens to your bond energy? Well, the bond energy goes down, meaning, right, when you have high bond energy, that means the attraction is really strong. When you have low bond energy, that means the attraction is really weak. So basically we have here is the bigger the bond length, the weaker the bond. All right. And then to kind of wrap this up, you have a couple of concepts here to kind of wrap in the same idea is the multiple bonds in bond energy. So double bonds have shorter bond lengths, but higher bond energy than similar single bonds. So for example, the CC bond, it's shorter, but it's stronger than the C single bond C. So the C double bond C is stronger than C single bond C. You can see that pattern over here on the right side as well. But I think that also kind of makes sense, right? When you have more bonds between atoms, it's a stronger bond. Finally, let's talk about this special case here about something called covalent network bonding. These covalent network bonds are kind of its own special category because instead of being like little molecules, kind of like we saw with sucrose or even water, in this case, some covalently bonded substances exist as a network of atoms rather than as molecules. So a couple of important examples here, diamond and graphite. This is actually diamond right here. This middle one's examples of graphite. You should recognize those substances. You can look right in here, all these atoms, right? There's no single molecule, right? There's no very obvious distinct grouping that represents the diamond. The diamond is actually just a giant network of covalently bonded carbon. At the same time, graphite, which is used in pencil lead, you can see right here, it has a slightly different arrangement. If you can imagine, first of all, these little shaded areas aren't really actually present, but they kind of help show you that it's kind of a flat structure. But you also have all these individual carbon atoms bonded in this way, in kind of what looks like little sheets stacked on top of each other. And part of the reason why the graphite works so well as a marking structure or marking substance is because as you kind of point, or as you kind of put the drag anyway, the surface of the graphite on a piece of paper, these sheets kind of get left behind, right? So they kind of shears off as you run your page, run the pencil across the page. Finally, the last example it's worth mentioning here is silicon dioxide. Silicon dioxide has a formula generically SiO2. And this right here, as you can kind of see, is an example of quartz. And a lot of times glass also is made of some SiO2, silicon dioxide. So even though SiO2 looks kind of like a regular old molecule, it turns out it's actually not really just a molecule. It's actually part of a giant network. And those have unique and particularly strong attractions, which gives quartz and glass its own unique sort of property that you wouldn't see with other covalently bonded substances. All right, that'll do it.